In this lesson, we're looking to perform the conversion from polar to component form in 3 dimensions. So we're going to look at going from our polar form, where we've got a magnitude, an azimuth, and an altitude, and converting into component form, where we're looking at the vector in terms of x, y, and z. Right, so I'll go through where these come from, but essentially you just need to remember the rules in the end. So if we start here with our magnitude and we look at that in relation to our altitude, so our magnitude and altitude, and we're looking at the size of the right angle triangle where we're looking at z and this diagonal base distance. Now, if we apply trigonometry, because we know it's a right angle triangle, then we've got an opposite hypotenuse and we've also got an adjacent hypotenuse. So we could say that cos of the altitude is equal to the adjacent, which is our base, over the hypotenuse, which is the magnitude. When we isolate the base, we end up with that being equal to the magnitude multiplied by cos of the altitude. We can do a similar thing with the z value. We know that the sine of the altitude will be z over the magnitude, because that's opposite over hypotenuse, and we end up with z being equal to the magnitude sine of the altitude. So we have here now that the base is the magnitude cos of the altitude, and that z is equal to the magnitude sine of the altitude. So if now we forget about the triangle with the altitude in it and we focus on the triangle with the azimuth, then we're looking at the azimuth x and y. So again, using basic trigonometry, we know that the opposite and hypotenuse will be sine. So if we go sine theta, the opposite is y, and the hypotenuse is a base. Now the base is, as we already calculated, the magnitude cos of the altitude. When we rearrange and isolate for y, we end up with y is equal to the magnitude cos of the altitude and sine of the azimuth. So now we've created a rule to calculate y using the magnitude, the altitude, and the azimuth. Now, if we do the same thing with x, we know that cos is adjacent over hypotenuse. We've got cos of the azimuth is x over the base, where the base is the magnitude cos of the altitude. So when we isolate the x value, we end up with the magnitude cos of the altitude, cos of the azimuth, calculate the x displacement, which means that our conversion ends up being going from this polar form into component form. Our vector will be in storage vector form x, y, and z, which will be magnitude of a cos altitude cos of the azimuth, the magnitude cos of the altitude for y sine of the azimuth, and then for z it's simply the magnitude sine of the altitude. Those 3 calculations allow us to perform the conversion in 3 dimensions from polar into component form. Okay, so we'll look at 2 examples, a simple and a complex one. Okay, so in this simple example, we're just looking to convert the vector A, which is in polar form, with a magnitude of 2, azimuth of 30, and an altitude of 45 degrees in component form. So we know that the magnitude is 2, the azimuth is 30 degrees, and the altitude is 45 degrees. So A will simply be equal to magnitude cos altitude cos azimuth, magnitude cos altitude sine azimuth, and magnitude sine altitude, which is going to be 2 multiplied by cos 45 multiplied by cos 30, 2 multiplied by cos 45 multiplied by sine 30, and then 2 multiplied by sine 45. So with or without the calculator, this is relatively straightforward. 2 multiplied by root 2 on 2 multiplied by root 3 on 2. Then we've got 2 multiplied by root 2 on 2 multiplied by 1/2. And then we've got 2 multiplied by root 2 on 2. So hopefully you do remember your standard triangles and you can apply them pretty quickly. So we end up with 2 root 6 on 4. We have 2 root 2 on 4 and 2 root 2 on 2, which can be simplified down to root 6 on 2, root 2 on 2, and root 2. So the vector A is root 6 on 2 in the I direction, root 2 on 2 in the J direction, and root 2 in the K direction. So pretty straightforward. Make sure you're fluent with your standard triangles, and that shouldn't be an issue at all. And so when we look at Bob's velocity relative to the rocket, it's going to be the velocity of the rocket subtract Bob's velocity. Now, the rocket, if we look now with the rocket and its movement along the ground, we need to be pretty careful, remembering that we need this in vector form, so we need it relative to this x-axis. So when we look at a south direction, which is where he's traveling, the angle from that x is actually going to be negative 90 degrees or 270 degrees. So that means that rocket's velocity is going to be 100. Its azimuth is going to be 270 degrees and its altitude is going to be 60 degrees. Now with Bob's velocity, again, he's going northeast, so never eat soggy wheat big, 45 degrees here, but what we want is from the x-axis. In this case, it ends up being 45 degrees as well. So his vector will be 30, 45 degrees, and 0. So we'll need to convert them into component form to continue. We've got 100 cos 60 cos 270 for the x, 100 cos 60 sine 270 for the y displacement, or the y velocity in this case, and then we've got 100 sine 60, and we're subtracting the vector, which is 30 cos 0 cos 45, 30 cos 0 sine 45, and 30 sine 0. So if we plug that into our calculator, we'll get the vector, which is negative 15 root 2 in the I direction, negative 50 take 15 root 2 in the J direction, and then 50 root 3 in the Z direction. Now we'll have to convert this back to polar form and then into bearings directions. So our magnitude will end up being square root of 13021.32 approximately equal to 114.11 meters per second. Our azimuth sits in the third quadrant because we've got a negative and negative value. So acute angle will sit between the x-axis and the line, and we'll be adding 180 degrees. So our azimuth is 180 degrees plus the acute, which is 180 degrees plus arc tan of the y value. We'll look at the positive version of that. So that's going to be 50 plus 15 root 2, and it will be over 15 root 2. Azimuth is approximately 253.4 degrees. Now if we want to convert that to a bearing, which is what we're going to need, it's going to be the remainder plus 90 degrees to come from north. So we're going 90 plus 360, take away 253.4, which works out to be 196.6 degrees from north. And then finally, our altitude is arcsine of z over the magnitude. So we're looking at 50 root 3 over 114.11 approximately. Well, from Bob's reference, the velocity appears to be 114.11 meters per second at 196.6 degrees from north, with an angle of elevation of 49.37 degrees. Okay, so obviously that example is quite complex and involves another number of understanding from Unit 1 vectors. You can see how it can be applied, and three-dimensional conversions can be part of bigger problems. Right, so that concludes the lesson on conversion from polar to component.